Welcome to This Explainer. Today, we're jumping right into the mathematics of random variables. We aren't just talking about blind chance here. Whether you're dealing with complex algorithmic modeling or tuning signal processing, we're going to look at exactly how we turn the completely unpredictable into something we can rigorously measure, map, and, well, master.
Here's our roadmap for today. We'll hit 1. The axioms, 2. Defining variables, 3. Flavors, 4. Measurements, 5. Relationships, and finally, number 6, the skeleton key. Let's get to it.
Starting with Section 1, the foundations of probability. Okay, so everything we do is grounded in these absolutely unbreakable mathematical limits. As an experiment repeats infinitely, as that n approaches infinity, probability actually stabilizes into a hard mathematical limit. It's like watching chaos settle into order. And right below that, we have Bayes' law, which rigorously defines conditional events. It basically maps out the probability of A given B by dividing their joint probability by the baseline of B. It's absolutely crucial stuff.
Moving on to Section 2, defining random variables. Now that we've got the ground rules, let's look at the cumulative distribution function, or the CDF. This is what anchors a random variable to a definite probability range. F of x represents the strict, hard probability that our variable x is less than or equal to a specific value, lowercase x. And since it's cumulative, it's always an increasing function. It climbs from exactly 0 at negative infinity all the way up to a perfect 1 at positive infinity.
So what happens when you take the exact derivative of that CDF? You get the probability density function, or PDF. This brilliant little equation gives us the probability density at any exact point x. And here's the really cool part. Because it represents literally all possibilities, the integral of the PDF across the entire domain must equal exactly 1. Makes sense, right? The sum of all probabilities has to be 100%.
Which brings us to Section 3, discrete versus continuous flavors. You see, the math fundamentally shifts depending on the flavor of the variable we're looking at. For discrete variables, things that take on finite, distinct values, we rely on discrete sigma sums. But for continuous variables that can span literally any value within an interval, we switch over to smooth integrals. So just remember, discrete jumps use sums, and smooth, continuous intervals use integrals.
Let's jump to Section 4, measuring moments and variance.
Okay, think of mathematical expectation as the physical center of mass for our probability distribution. We denote this by mu sub x, or E of x. It's basically the statistical anchor around which all those unpredictable random outcomes tend to cluster. The mathematical symmetry here is just perfect. To find our center of mass, we multiply every possible value of x by its exact probability or density, and then we just aggregate them all together. And as we just talked about, we use a sum for the discrete variables and an integral for the continuous ones.
But hey, just knowing the center isn't quite enough, is it? We need to know the spread, and that's exactly what variance does. Mathematically, it's the central moment of the first order of degree 2. We just subtract our mean from each value, square that difference so it's always positive, and multiply by the probability. Oh, and a quick side note, if you take the square root of that variance, boom, you've got your standard deviation.
Moving right along to Section 5, joint probabilities and relationships.
This quote right here is essentially a golden rule in statistics. The joint probability density function is the master blueprint. If you have the joint probability of variable x and variable y interacting, you hold all the statistical information about their relationship. Literally everything else can be derived from this. To picture this, for discrete bid-dimensional variables, this joint probability maps perfectly onto an m by n matrix. Every single intersecting cell in this grid isolates the exact joint probability of event x sub I and event y sub j occurring simultaneously. It's like a giant puzzle perfectly laid out.
Now, to mathematically measure how these two variables move together, we use two main tools. Statistical correlation serves as the raw second-order moment. That's the expected value of x times y. Covariance, on the other hand, is the centered second-order moment. It evaluates the expected value of their combined differences from their respective means.
So what's the magic number here? It's 1. By taking that covariance and normalizing it, dividing by the standard deviations to strip away the scale, we get the correlation coefficient. At exactly 1, or -1, the variables are locked in a perfectly linear relationship, no way around it. But if that number hits 0, they are completely uncorrelated.
And finally, we've reached Section 6, the characteristic function.
This is the statistical skeleton key we promised. The characteristic function is profound. By taking the expected value of an exponential function with an imaginary number, we are effectively performing an inverse Fourier transform right on our probability density function. It's a real game changer because it encodes the entire distribution into a brand new, incredibly useful mathematical domain. Let's watch the statistical magic happen. First, we perform a Taylor series expansion on that exponential function. Next, we take the derivatives, setting u to exactly 0. Because of this specific transformation, every single statistical moment, the mean, the variance, the skewness, literally falls perfectly out of the equation. Differentiate this one single function, and it yields every secret the random variable holds. It's the whole shebang. So this leaves us with a really fascinating paradox to close on. Given the absolute precision of the math we've explored today, where these functions elegantly encode every possible statistical moment, have we truly eliminated randomness from the universe? Or have we just built the perfect mathematical cage to map its boundaries? Think about that next time you flip a coin. Thanks for tuning into this explainer. I really hope it sparked some curiosity for you today.